Hello and welcome to Homework 1 for Computational Methods, titled Vectorization of Jacobian for an Asarian 3D Plane. So in this homework, we're going to be plotting a helical pipe with these parameters in t, and with a cross-sectional radius of 0.5. So this will be a 4-part series. In part 1, we're going to create a function that can calculate the Jacobian of that central helical curve, and then compare that to Jax's inbuilt automatic differentiation. So the reason why this is important is because we're going to then use these Jacobians in the following parts of the series. So first and foremost, what is a Jacobian? So Jacobian is simply a vector of the partial derivatives of a function, or more of several functions, in several variables, all defined in a matrix. So, for example, in this function with two variables x and y, with these two function given these two parameters, calculating the Jacobian of this would yield a 4x4 matrix with the first column being the partial derivatives with respect to x, and the second column being the partial derivatives with respect to y. Then the first row is the partial derivative of the first function, and the partial derivative of the second function is in the second row. So in our example, our helical pipe has these three parameters in the x, y, and z direction. So in our case, we have only one variable that we're going to be doing our derivative with respect to, which is t. But we have three parameters. So our Jacobian is going to be three functions. So it'll be 1, 2, 3 rows. But since we're only doing derivative with respect to t, we're only going to have the one column. So let's go right ahead and start coding it. So first thing we're going to need is we're going to need to import some of our libraries that we're going to need. So first one we're going to need is NumPy. Then we're going to need to import Jax. Then we're going to want to import Jax version of NumPy as JMP. And we'll leave it there. So first and foremost, what we're going to want is we're going to create a function that can plot this curve, just so that we can see the curve in what we're going to be doing. So let's define a function, call it curve, and I'll pull its variables later. So our curve is going to give us, the idea behind this is we're going to calculate our x, y, and z point at specific t's as the curve goes. So what we're going to do is we're going to put these values in an xyz array that we're then going to later plot each point in a three-dimensional graph. So we're going to call this just xyz, and we're going to make an array. Then what we want is we want to first do our x. So x is 3 times cosine of t. So our x is going to be r times Jax NumPy cosine of w times t. So these variables I'm putting in are going to be variables that we're then going to give the curve. So actually, let's do that now before we forget. So we're going to give it R, W, T. So then we want to do 3 times sine t for y. So our y is going to be pretty similar. So r times jmp dot sine w times t. Then our z value is 0.4 times t. So let's just call that mz for slope of z times t, which then means we also have to give mz. Then we're going to return xyz. Okay. So now in order to use this function, we have to give it values for r, w, m, z, and t. So as an r is equals 3, w equals 1, mz equals 0.4, and t equals, well, since it's an array, what we want t to equal is we want t to equal an array itself. So let's do np dot linspace. So what this function is going to do is it's going to create an array that gives us evenly spaced numbers over an interval. So we're going to start that interval at 0 and end it on a nice, let's end it on a number that's the trig functions are happy with. So usually a multiple of pi. So we'll do 6 times np dot pi. Okay, so that's the stop interval, and then we want, I don't know, 54 of them. So what this will do is it'll create an array for time from 0 to 6 pi with 54 evenly spaced numbers all the way across. Okay. Now let's just check our function, make sure it works. So we give it r, w, mz, and t. Okay. So we just generated values, and for this first row of the array are all the x values as we told it. The second one's y, the third one's z. Cool. So close that. Let's just plot this just to see what it looks like. So in order to plot it, we have to import from plotly subplots import make underscore subplots. Okay, so we'll need that. So we'll give it figure, generic figure equals make subplot. Then we want to give it rows equals 1, comma, columns equal to 1. Alright, now we're going to add scatter 3D. Then x, we're going to specify that our x values are going to be our x, y, z. Then we'll want the first row, but every column. So 0, comma, since it's Python, we start indexing at 0. Y equals x, y, z at 1. Z equals x, y, z at 2, comma, colon. Then we want to update layout. I'm going to do equals 600. 600, height equals 600. I'm going to do template equals flatly dark. Hopefully that should work. Now we should probably actually generate XYZ first. Good, this one is on the way. Let's generate this block. Cool. So here's our helical curve. Actually, we could probably get rid of the now it gives me the helpfulness. All right, let's me check. So if we want to get rid of the dots, then we have to do mode equals lines, maybe? Let's try that. Cool. So I got rid of all the points and just made a smooth figure. Okay, so there's our figure. Actually, let's separate these. Okay. Now, this is our figure, and that's all well and good. But the actual homework, or the actual part of this homework, wants to know about the Jacobian of the function. So make this called Jacobian section. And we're gonna close this curve, add some code here. All right, so this is our curve. Now, we know that the Jacobian is a set of partial derivatives. So, what is a derivative, if as you remember from calculus days, is basically a limit of a function of 2 points in that function that are extraordinarily close together, and the difference of that, well, divided by that difference, and that will give you the slope of that function. So we're going to create a function that emulates this in order to test it on our function at various points. So that's defined as Jacobian underscore test, and we're gonna, within that, we're gonna just try to find forgot. So we're gonna give it the function, and that function is gonna be our parameter. Then within that function, we're gonna create another function that will actually be doing the test for us. So in that one, we're gonna give it an x value. So our x value is going to give us like a numerical point that is going to be equal to our partial derivatives at that point. So we're going to give it x, and then we're going to give it a dx. So in this derivative, our dx is going to equal this h here. So we'll set that equal to 1 e negative 8. So very small. Now, the first thing we're going to need to do is we're going to need to create an array to put our values in. So let's do j. Let's just make it j equals, let's use mpy.zeros. So let's make an array of zeros. Now we need to give it a shape. So let's come back to that shape, because that'll be, because the shape of the Jacobian is dependent on how many functions you have and also how many variables you have. So we only have one variable to start. We only have one variable that we're going to test, so we're going to give it a shape of, oops, what did I do? We're going to give x dot size, and then we want f0 dot size. And now what is f sub 0? So f sub 0 equals the function solved at x. So the function that we give here, we're going to solve it at x. And that'll, oh. And then what we're going to need to do is we're going to need to make a for loop. So for I in range of x dot size. So what we're going to do is we're going to run a for loop for each x value we have. Since we only have one variable that we're doing our derivatives over, we can get away with just using x. So for I in that range, we're going to then do this limit. So we're going to want to define a new variable, x tot, which is going to be equal x plus dx. Then what we're going to want to do is we're going to use this limit. So we're going to put it in our J matrix that we made before. Put in that matrix. We'll give it its index in a second. But what we're going to want to do is we want to do our function solved at x tot minus our function minus f0, which is just the function solved at x. All that divided by our dx. Okay. And then we'll return our j. And then, let's see. So when given, so since I've done this a couple times, I know that if I run it as is, our f0 will come out as a single float, as a single value instead of a one-dimensional array. So what we're going to want is we're going to want to set our x equals at least 1d of x, and f0 I think we want to move this ahead, so let's just slide it up here. Then we want to do f0 equals at least 1d f0. Alright, so we need to give it a All right, so you're in it, and we forgot to put this in. So for this one, we want to do, let's try this, right? So we want to give it, we want to put the values in filling column 1. Well, filling column I, really. So what we want to do is we want every value we generate, we put it in column I, just down the rows. Okay, and then I think we also want to define this as, give it this index also. Which in case we should probably x tot equals p dot, I think it's copy x. Okay, so we have that, we have this, we have that. Let me see if I've forgotten anything. We have to, we forgot to return our main function, so we want to return that. So that should work. Now let's test it. So we want to do Jacobian underscore test. Now we have to give it a function. So the function we're going to give it is our curve. But we have to specify what what the variable that we're going to be changing is going to be. So to do that, we're going to use our lambda function, lambda t, comma, or colon, sorry. And we're going to do curve r, make sure we got these right, rw mzt. Let's run that. Okay, so no errors. That's good. That's a good sign. So I'm going to set this equal to Jack. Then let's do Jacob. Let's start at 0. All right, so we got an error. So not happy with this. All right. So it looks like we're trying to do. Let's tell this that we want to do. Let's try that. Maybe that'll work. All right. So it ran, but those aren't the right values. What we would expect to see is one of the two. The value we'd expect to see. Well, actually, let's show you. So let's do Jacobian. And we'll copy and paste this. We'll make that Jack's Jack. And Jack's Jack at 0. Jack's Jack at 0 equals 0, 3, and 4. So as we'd expect, one of the trig functions at 0 came out with a value of 0, sine. The cosine came out with a value of 1 times r, which is 3, so 3, and then mz is 0.4. So that means something in our function is wrong. So let's dive a little deeper into it. All right, so diving into it, let's tell us to put it at 0 instead of I. Still not it. Okay, so let's look a bit closer. So we have function x toe, which we said should be x plus dx minus our initial. So parentheses right divided by our dx gives it to that. Now, should I tell it? That's a new one. Okay, so I ran that. So let's run with this last one. Positional argument. All right. So I think what it wants is the t up front. So why don't we do that? Let's put the t up here. Which of course means that we'll have to do the same for this guy. Now we'll have to fix this here, of course. So t up front, and then we will just run everything. Make sure we run them all. Can ignore that for now. No, we can't. Okay, so that didn't. All right. Don't know why I just put here. Let's see if I have these in the wrong order. There we go. So as you can see here, we just had these in the wrong order. So we put in 0.3.4, which is right the same as we got here. So as another test, let's just run it at 1. Run it at 1. All right. So still not quite there yet. We are running into other errors, I see. So no, that's right. That's right. It's the right size. All right. So I forgot to identify make Jax 64-bit. I forgot to make Jax 64 bits, and normally Jax is 32-bit, and that might be the error. So let's see. Here, 64-bit. So we're going to copy and paste this, and we'll run everything. What's that? Voila, sweet. So that was all our error was. So comparing these two, and I can again show it at 0. Comparing these two functions that we made, they're exactly the same. So that's all the Jacobian on our thing is doing. So join with me in part 2 for the next part of the video, where we're going to use the Frene-Serre formulas to actually start to build the plot of the pipe instead of just a single line.